If you've been paying attention to how large language models work under the hood, you know that compute isn't the only bottleneck. There's a hidden monster that wakes up during inference, especially when you ask an LLM to read a long document or write a lot of code. It's called the KV cache. Every time the model generates a new token, it needs to attend to all previous tokens. To avoid recalculating everything, it stores the key and value vectors for every past token. But as the sequence length grows, this KV cache consumes gigabytes of VRM. It scales linearly with context length, and eventually, you hit a memory wall. Today, we're looking at a paper from researchers at Google and NYU called TurboQuant. It proposes a mathematically beautiful way to compress these high-dimensional vectors down to just 2.5 or 3.5 bits per dimension with virtually zero loss in model quality. And it does this without any retraining. To understand how, we have to talk about the geometry of high-dimensional space. The goal of vector quantization is simple. Take a continuous vector x in R to the d and map it to a finite codebook of discrete points, so it can be stored using just a few bits. But how do we measure if a quantization is good? In most engineering fields, we care about minimizing the mean squared error, the geometric distance between the original vector x and its quantized version q of x. But in transformers, the attention mechanism is entirely driven by the inner product between query and key vectors. Here's the catch. A quantizer that optimally minimizes mean squared error inherently introduces a bias into the inner product. If you just naively round your vectors to minimize distance, the attention scores will drift. The softmax will amplify that drift exponentially, and the LLM's output will degrade into gibberish. TurboQuant solves this dilemma in two elegant stages. Let's look at the first stage, which the authors call polar quant. In LLMs, vector coordinates often have extreme outliers. Some attention heads produce massive activations in specific dimensions. If you try to build a universal scalar quantizer for these coordinates, it fails because the distribution is too unpredictable. The researchers apply a completely random orthogonal matrix to the input vectors, a random rotation in high-dimensional space. Why? Because of a beautiful phenomenon in high-dimensional geometry. When you randomly rotate a vector, its variance spreads out evenly across all dimensions. Regardless of how the original data was distributed, the coordinates of the rotated vector follow a highly predictable, concentrated beta distribution. Furthermore, in high dimensions, these coordinates become nearly independent of each other. Because the geometry is now mathematically well-behaved, we can simply apply an optimal scalar quantizer to each coordinate independently. This gives us a highly efficient MSE optimal quantization. No data-dependent calibration or fine-tuning is required. It's completely data oblivious. But remember our dilemma. This MSE optimal quantizer is biased for inner products. The original vector x is equal to its quantized version plus a small residual error vector, r. When we take the inner product with another vector y, the error term r.ei doesn't necessarily average out to zero. To fix this, we need to store information about the residual r, but we don't have many bits to spare. We just want to preserve its inner product properties. Enter the quantized Johnson-Lindenstrauss transform, or QJL. The Johnson-Lindenstrauss lemma is a famous result showing that you can project high-dimensional points into a lower-dimensional space while preserving distances and angles. TurboQuant takes the residual r and applies a 1-bit quantized JL transform. By spending just a tiny fraction of a bit per dimension on this QJL representation of the residual, they create an unbiased estimator for the inner product. You get the best of both worlds: minimal geometric distance from the MSE step and preserved attention scores from the QJL step. What makes this paper stand out isn't just the clever engineering, it's the rigorous math. The authors provide a formal proof, rooted in Claude Shannon's source coding theory, establishing the absolute information theoretic lower bound for distortion in any vector quantizer. They proved that TurboQuant operates within a tiny constant factor, about 2.7, of this absolute theoretical limit across all dimensions and bit widths. It is mathematically near optimal. And in practice, On LLM benchmarks, compressing the KV cache with TurboQuant down to 3.5 bits per channel results in absolute quality neutrality. You get the exact same performance as uncompressed 16-bit floats, but your cache is over 4 times smaller. Even at 2.5 bits, the degradation is marginal. And because it relies on simple rotations and scalar operations, it runs incredibly fast on modern hardware. TurboQuant shows us that the solution to hardware bottlenecks isn't always just building bigger chips. Sometimes it's about looking at the geometry of your data, applying a random rotation, and trusting the beautiful mathematics of high-dimensional spaces. If you want to dive deeper into the proofs regarding the beta distribution or the QJL transform, I highly recommend reading the paper. Link is in the description. Thank you for watching.